Okay, so we're supposed to derive the formula for the area of a circle. So let me maybe just start by just giving you that formula. So this is what we're supposed to come up with. We're supposed to be able to say, okay, here we go. Got the computer moving really slow on me here. That x minus h squared plus y minus k squared is equal to r squared. Does that look familiar to you at all? Some value here squared. Oh, that's not equal to. That should be plus. Some value there squared is equal to a third value squared. You recognize that at all? That is Pythagorean Theorem right there. If I've ever seen it, that is Pythagorean Theorem. Okay, so what we're going to do is we're going to, let's see, let me put that over here somewhere. Let's see where that comes from and how we could derive it. So here we have a circle, okay, and I'm just going to place a point on it, but I don't want to use that point. That point, if I move it, it will change the size of the circle. I don't want to change the size of the circle right now. In fact, I will put another point on that circle. So the idea, the concept is that for any circle with a center here and a point on the circle, there is going to exist a third point inside the circle somewhere, such that we can make a right triangle. Right? We want to make a right triangle, and then we can use Pythagorean Theorem to find this length, just like we did the distance formula, right? Remember in the plane that we did the distance formula by saying, well, we want to know how long AC is, so let's figure out the leg here on the x-axis and the leg here on the y-axis, and then we'll know what the radius length is, right? So that's basically what we're going to do. So we'll construct this. Now I want you to watch close because you're going to do this construction as well. I want you to make this construction as well, okay? So what we're going to do is we're going to create a parallel line that's parallel to the x-axis and goes through A. And another parallel line is parallel to the y-axis and goes through C. And then we can find our intersection point. Where do those 2 points intersect? Right there. Now we can hide those lines. We don't need them. We don't need to see them. They exist, but we've just, used these buttons here to make them disappear. We can form this right triangle here. Now I know these are right because this was parallel to the x-axis and this is parallel to the y-axis. By definition, the x and y-axis are set together at 90-degree angles, but to verify it, I could just measure, it's a 90-degree angle. Okay, not a big deal there. We put that measurement down there. Okay, so now what's kind of nice about my little model here is that as I move C around, you can see that there's going to be always a right triangle. Now, when we get over here into this quadrant, it was measuring the outside of that angle now, so that's 270. So the inside has to still be 90. So it's still validating or verifying that it is a 90-degree angle. Okay, so this point exists D so that we can make a right triangle. If this were, horizontal, there is no right triangle here. And we'll talk about what happens in those situations. And in a vertical situation, the right triangle's gone. We have no measure there. We'll talk about those specific situations when the point C is located here. So now let's give some different letters here. Let's call A, I don't know, let's call this one point C. And the reason for that is because it's the center of our circle. And C1 here, let's rename that, and we'll call that point, let's see, P, because it's a point on the circle. I don't know why. We'll just call it that. And we'll call this point D. Well, let's just rename this to, point X, because it's moving around a whole bunch, just for that reason. All right. Now, how would we come up with this formula? Well, let's see. We would start by saying that we know that the measure of CP is equal to the radius by the definition of a radius. In other words, it is the segment connecting the center of a circle with a point on the circle. Okay, so we know that CP is equal to the radius. That's the first thing we'd say. So now what's the measure of CX? Well, we know that CX here is going to be equal to the distance between point C and point X. Okay, but let's not use these actual measures for let's not use these actual coordinates for C. See, C is at 4.54, 4.52, but I could move that. See, and it would adjust the circle. I don't want to do that. I don't want it to be just because it's here. So we use a, oh, I forgot something else on here. This is where R is equal to the radius and HK are the coordinates of the center of the circle. So this is the formula. The formula has H and K, this value H and this value K, as the coordinates of this circle, of the center of the circle. So for us to derive that, we're gonna have to say that C is also, point C is at HK. We'll just say it's at HK. So whatever value we have for X and Y, they're going to be called H and K. Well, since this is at Y on the Y-axis, this is at K value, so this would be H on the X-axis and K on the Y-axis, right? So this point X is also going to be at K, right? It's going to be at K on the Y-axis. But where would P be? Well, P is just going to be some point, could be any point X and Y on this circle, right? So let's give it that value there. So P is at X comma Y. Any point X, Y on the circle, there is P, okay? But what about this now? Well, remember, we said that the Y value of this X is the same as the Y value of C, because remember that I've made it so that it always stays horizontal to C. I'm picking a point that's going to always be horizontal to C, so it has the same Y value. So what would the value for Y be? Well, we know that, point X is going to be at some value, we don't know, we'll put a space there, and at K, because we know that it has the same Y value as point C, right? Okay, but then what about its X value? Remember that it always stays vertical to point P, right? So it's on a vertical line here, so its X value is always going to be the same as point P. So if point P is at X, Y, then point X would be at, then point X would be at X also for its X value. So we would say that it's at X, so that it's lined up here, K, so it's lined up there. And wherever I move this, let's verify that that's the case. Over here, I've got point P. Point P is at 5.8 on the X-axis. And guess what? Point X is also at 5.8 on the X-axis. They remain constant. How about C and X over here? C has a Y value of 4.64 and X has a Y value of 4.64. So you can see that no matter how I move this, the point P and point X have the same X value. Point C and point X have the same Y value. So that's the point that we're looking for, the point that has the same X value as P and the same Y value as C. So now let's just do Pythagorean Theorem. So Pythagorean Theorem says that we would go leg squared plus leg squared equals hypotenuse squared. And in this case, we call it L squared plus L squared equals the H squared. Well, in this case, remember our hypotenuse in this circle is always going to be CP. And we already verified that CP is the radius. So we can substitute by substitution, okay, L squared plus L, squared, oh, that's a plus, sorry, squared plus L squared is equal to the radius squared. Okay, that's by substitution. Okay, now what's next? We got to figure out what would the length of this be. So let's put that in there. Okay, so the first leg is going to be leg CX. So leg CX is going to be equal to the square root of, and it's going to be, remember, x minus x squared, so that would be x minus h squared plus y minus y squared, and that would be k minus k. So we're going to go k minus k squared. Okay, so that means it's equal to, which is equal to the square root of, now we have x minus h squared, squared, plus 0 squared, because k minus k is 0, right? Which is equal to the square root of x minus h squared, right? Because 0 squared is 0 if we add that in. And if we take the square root of a square, we equal to the, we're only going to take the positive value, but we'll just say that's x minus h, which makes a lot of sense, okay? The square root of a square, those would cancel. We have positive and negative possible values here, but the reality is that we're looking for a length, so we're just looking for the positive, whatever that is. We could put the absolute value of, I probably ought to put that in there so we could do that. The absolute value, where'd my up and down line, man, I've forgotten this. Is it here? The absolute value of x minus h, okay? So that's the length here. In other words, the positive value. Even when it's going over here, if I end up with a negative value here when I subtract, then it's still going to say just make it positive because we're talking about a length here. So that's leg CX, okay? So now we're going to do leg PX. So here we go. Leg PX. And by the distance formula, that's equal to the square root of, and we're going to go x of p minus x of x. So that is x minus x, right? Squared plus y of p minus y of x. So that's y minus k squared. And we're taking the square root of that, so that is equal to the square root of, now x minus x is just 0 squared plus y minus k squared, squared, right? Which is just basically equal to the square root of, and now we just have y minus k squared, right? Which, when you take the square root of the square, we're in the same situation before. We go, it's equal to the absolute value of y minus k. Okay? So that's basically what we have here. So now think about that. I mean, we take whatever y value this is, we subtract k from it. You know, because if we've come from the y-axis up k units, and we're going to go start there and go all the way up to y, we just find the difference between y and k, that's the length. Same thing here with the x. We go from the x over k units and then going to keep going until, or I'm sorry, over h units, keep going until we get to x units, then the difference x minus h is how long this leg is. So, you know, we can see it logically and we can calculate it algebraically. But now by substitution, we're going to put this in for one of the legs and this in for the other leg. And once we square it, because we're going to square these legs, guess what we have? We have here, we don't have to use, because we're going to square it, it's going to make it positive, so we don't have to use the absolute value anymore. So we're just about done here. We would say, therefore, the formula for the equation of a circle by substitution we get, and it's going to be x minus h as the first leg, and we'll square it, plus y minus k as the second leg, and we'll square it, is equal to the radius squared. Okay? So there we have it. We've derived it. Now I want you to see this actually. So I'm going to just pause this real quick and show you on my okay, so I'm going to make a new document here, and I'll just say no. And here we go. I'm going to make it a graph. And what I really like about these calculators, a lot of things I like about them, but one of the things that I really like about them is it allows us to enter the formula directly using our menu here. So if I go menu, graph entry edit, and I want to put in the equation of a circle, notice that it says, hey, do you want to put it in its center form? X minus h squared plus y minus k squared equals r squared. Well, that's kind of nice here because I can just pick h and k, which are going to be my coordinates for my center, and the radius that I want. So if I want, let's say I want my center to be over 3 units and up 4 units. Let's go over a little more. Let's go over 5 units and up 3 units. So I would put 5 units and up 3 units. And then if I wanted to have a radius of 2, the center will be at 5, 3 and have a radius of 2. And there you have it. Okay? The center's at 5, 3. Okay? The radius is 2. So from 3 I come straight down to 1. That's my radius. Okay? So that's how that works on the calculator. You just remember h and k. Notice that I wanted positive 5 and positive 3. So I had to make it x minus 5, y minus 3. If I wanted negatives, I'd have to change that to plus, right? And I would put in y minus a negative 5, or x minus a negative 5, and y minus a negative 3. Let's see how it looks on the GeoGebra app. We can do it on GeoGebra too. So let's just put in a new one of these, and we will swing this around. So I'm going to put in right down here, I hope you should be able to see that. I could say that x minus 5 squared plus y minus 3 squared is equal to 2 squared, which would really be 4. And look, here I have the same thing. There's my circle, has a radius of 2 squared, which came out to 4, but the radius would be 2 here, right? And it has a center at 5, 3. Okay, so there's 5 and 3. The center's right there. Okay, so you can see that that formula works for the formula of a circle. And now you're going to want to watch. You will need to derive that formula doing the work that I just did, where you will construct first your circle, and then you'll explain how there's a point. There's always a point inside the circle such that we can make that right triangle, right? And that this leg is equal to x minus h, and that leg is equal to y minus k, and you show the work. And this leg is equal to the radius. And then you can use Pythagorean Theorem to derive this equation. Okay.